Hey guys, welcome to the lesson on waves, and we're going to go into a lot more detail in this one this time. We've got three goals in this lesson, guys. The first one is, I want you guys to describe the properties of waves, be able to differentiate between transverse and periodic waves, and you'll solve some problems that are involving waves. So basically, waves, waves, waves. Okay, well first off, what are waves? Well, most of you guys know what they are intuitively. You know what they are because you've probably seen them before, you've heard them talked about before, but we're going to go into some more detail about what they are. Basically, a wave, according to physics, is motion is caused by some kind of a disturbance. So like a rock being tossed into the water would create waves because it would cause a disturbance like the one you see right here. Now, wave is just energy moving from one location to another. So when you see a wave, what you're really just seeing is you are seeing energy that is moving from one location to a different location. Now, it does this through something we call a medium. A medium is a substance that the wave has to travel through. Now, not every single wave is going to be this way. Some waves are not going to operate like that. The waves we're going to talk about in this lesson today, though, are ones called mechanical waves. And these are waves that are going to be formed inside of a medium. So things like air and water are good examples of mediums that waves can travel through. Now, waves come in two forms. The first kind of wave is called a transverse wave. A transverse wave is where the particles move in a perpendicular fashion. Now, when it says perpendicular, it's meaning perpendicular to, imagine this is a straight line, you know, my AP drawing on computer skills. So this particle is going to be moving perpendicular to essentially the center point here at X. And this is going to be a transverse wave. Now, in this case here, there are some key terms you have to know to be able to describe a transverse wave. The first one is a crest. This is going to be the top of the wave right here. The second one is going to be the trough. The trough is going to be the bottom of the wave right here. And the last one is going to be the wavelength. The wavelength is the distance between two different crests. Now, it can be either the crests or the troughs. It doesn't matter. As you can see here, they're both going to be equal to the wavelength. And finally, the amplitude is just how far down it's going to be going from the center point. The second type of wave is called a longitudinal wave. This is a wave that moves in parallel to the line of center. So sound is a good example of this, and so are springs. Springs are another example, as you can see right here. Basically what happens here is that a part becomes compressed, a part becomes stretched, and then compressed and stretched. So if you take a spring and you begin to push it up and down, you create a longitudinal wave, you're going to get this pattern that looks a lot like this, as the energy is being moved parallel as it goes down the wave. Now the thing is, though, when you look at this in terms of density, as the wave moves through the medium, even though it's considered to be a longitudinal wave, it actually looks pretty much the exact same as terms of the other type of wave, the transverse wave. Because you see here, we have x1 and x1, x2 and x2. As you can see, if you compare the density, so how compact the spring is right here, it ends up having the exact same shape as the previous example. Now, there are some key terms here you have to understand waves. The first one is called the period. This is the time it takes to complete one cycle. The second one is called the frequency. This is the number of waves that pass a particle in a second. So here's a quick little example of what this would look like. If you look right here, you have the frequency is going to be how fast it's going up and down. The period is going to be how long it takes to go from here to here. And here's a good example of the next key term, which is amplitude, which is the frequency. You see how the frequency here is changing between low, medium, and high. You can see that the higher the frequency, the faster and the more waves you can fit in the exact same time period. So higher frequency waves get more periods over time. Now the last one is called wave speed. Wave speed is frequency times wavelength. Basically, it's going to be telling you how fast a wave is going to be moving through a medium. Now, the speed of a wave oftentimes depends upon the actual medium that it's traveling through. And you're going to see what that means here in a second. So here's a sample problem. A piano emits frequencies that range from a low about 28 Hertz to a high of about 4,200 Hertz. Find the range of wavelength in air attained by this instrument when the speed of sound is 340 meters per second. Well, here we have, this question is actually two questions in one. So the first thing to understand is you're not just going to be solving one problem, you're going to be solving two problems. One for 28 Hertz and one for 4,200 Hertz, with the constant being the speed of sound. And the speed of sound is always the same. Excuse me. So here we have the velocity of sound is 340 meters per second. The first frequency is 28, and the second frequency is 4,200. So solving for the first wavelength, we find out that 3,400 equals a 28th times wavelength 1. This is equal to 12 meters. That means the wavelength on the 28 Hertz is going to be 12. On the other one, though, it's going to be 0.081. So what this here shows you has, as you increase the Hertz, you're going to be decreasing the wavelength of the wave. Now, this next idea we talk about is something called wave interference. Wave interference is the idea that waves can pass through one another, unlike a physical object. So, let's say that Mr. Russell is running down the hallway at full speed and I run into Prince. Now, if I run into Prince, we're going to hit each other. And I can't pass through him. I'm going to bounce off of him, and both of us are going to be hurt. Waves don't do that. Waves are able to pass through each other, unlike physical objects. When you see this, it creates something we call superposition. And this picture right here is a picture of superposition, because the waves are occupying the same place at the same time. So super means a lot, and position means, well, position. So it's just a lot position, or in this case, they're in the same position. Now, this causes what we call interference. And interference comes in two types. The first one's called constructive. This is when waves are going in the same direction and they combine. So right here you have a wave that is moving in this direction and a wave moving in this direction. As the two of them come together, they combined and form a giant wave. This giant wave is a combination of both waves combined. If you go back to the previous picture right here, the giant wave would be an example of this really dark band right here in this picture, because they're combining together and they're forming the exact same wave. What happens afterwards, though, is the waves then split apart and go back to being their same size. So the waves temporarily combined right here, and then they break apart right here. The waves don't actually combine. What happens here is that the waves just temporarily pass through each other, and when they pass through each other, they strengthen each other in constructive interference. The second kind is called destructive interference. This is the opposite. This is when the two of them are going in different directions and they have different locations here along the y-axis. When the two of them come together, you get a wave that is a lot weaker in this case. This wave here, when combined together, is going to make a much smaller wave. But, as you can see here, they're going to break apart and they're going to continue on their merry way. This is called destructive interference, and basically causes the strength of the wave to decrease. There's a couple other ideas about waves here too. One of them is called reflection. With reflection, a wave is going to bounce off a fixed point and it's going to invert and change direction. What that means is that a wave is going to travel down this direction here. It's going to hit the fixed point here, and it's going to bounce back. Now, it can also do what's called reflecting, which in this case here is going to go down this way, bounce off the thing, and it's going to reflect in the other direction with the opposite in its trough. So here it's going to have a crest, and here it's going to have a trough. What's the difference? The difference is that with this here, the attachment point is able to move with the wave. So the here is able to actually go up and down with it. Right here though, since it's directly attached to it, it's not able to actually move up and down as it gets there, so it's going to hit this and bounce back in the other direction. So this next idea is really hard for me to explain, guys. So I'm going to try to giving a video. I've stolen this from YouTube, and I'm going to go ahead and jump around this video real quick to show you what they've done. So what this girl here has shown is a type of wave. If you look here, you get a wave where the two waves form almost two different crests and troughs. If you keep on going farther into the video, you'll notice that she can increase the frequency of the wave, and what's going to happen is now we have three troughs and three different waves. And she can even go more than that, and she can create a situation where you have four different waves by increasing the frequency by a great deal. What is this? What's going on here? Well, we call this a standing wave. A standing wave is a wave pattern where two waves of the same frequency, wavelength, and amplitude travel in opposite directions. Now, to understand a standing wave, you have to understand two key terms: nodes and antinodes. A node is where things are equal to zero, an antinode is where displacement is at its highest. So in this case right here, this would be a node that I've circled right here. The antinode would be the location right here on the screen. The antinode is going to be the highest point. The node is going to be the lowest point of a standing wave. And that's basically it for this chapter, guys. What I want you guys to do today, while I'm gone, is three things. The first one is I've done the standard thing. I've posted some quick practice problems for you guys that you can complete. I will be posting the answer key to this in a later date. Next, when you're done with these, I would like you guys to make sure that you email me your supply list for your experiment. I'm going to need this to pick up anything this weekend. If you do not get to me your supply list, I'm going to assume that you aren't going to want anything. And if that's the case, that's fine, but it means you're going to have to do something with the stuff here at the school, or you're going to have to get all of your own equipment. And finally, what you're going to have to do here is that you're going to need to work on a PhET lab. Now, the lab I've created, or I've chosen for you guys, is a pretty simple lab, but it's a way to play with waves and see how they work, because we don't have the tools to do it here. This lab can be done on your iPads, and it can be done on your computers. It's one of the few that is able to do both. And that's it. You've got three things to do. This one should come first, followed by making sure you have your material list to me as second. And then finally, if you get those two things done, you should work on the PhET lab. If you don't finish the PhET lab, don't worry about it. I'll give you some more time on Monday if students aren't done with it. Sorry, not Monday, Sunday. I will give you guys more time on Sunday to work on the PhET lab if you are done with it. And that's it. And teacher person, whoever is subbing for me today, feel free to leave these directions here on the board so you can just freeze the projector and students can look at this and see what they're supposed to be doing. And everything on here is on Edmodo, so students can hop onto Edmodo and access it from there. Thanks, guys. Have an awesome rest of your day. And as always, sorry I couldn't be there. I will talk to you guys later.